All right, let's start looking at some things that we can do with the Jacobian. Sorry, that was some other stuff I was working on. Let's pull here. Do example 3 in the text here. We have 0 to 1, 0 to 1 minus x, square root of x plus y, times y minus 2x squared dy dx. And if we look at this, let's see, 0 to 1, so it's going in x, so it's going over to here, and 0 to 1 minus x, y equals 1 minus x, is a line starting at 1, when x is 0, it's 1, when y is 0, this is at x equals 1. So that's the region we're looking at here. Let's see if that's our region R that we're integrating over, and this is the function that we're integrating over that region. So what we want to do is look at what we can substitute for here. And so a suggestion would be to start with u equals x plus y, and y and v equals y minus 2, or y minus 2x. All right, we take these pieces and turn them into u and v. So whatever we're integrating over should be smoother. So we need to algebraically then figure out what x and y are. So what we want to be able to do then is, let's look at x equals y minus u, and y equals v plus 2x. So x equals v plus 2x minus u. So negative x equals v minus u. I'm off by, let's see here. Let's try to get the algebra right here. I'm going to do this substitution. Y equals v plus 2x. So u equals x 3x plus v. Therefore, 3x equals v minus u. No, u minus v. And x equals u over 3 minus v over 3. That's better. I like that. And now I want to find y. A nice way for getting y. Let's see here. Let's see. If I solve this for y, I get y of y equals v plus 2x, and v in terms of, don't want to, I had a nice easy substitution back up here. I want to do a nice similar easy substitution for y. So I changed this for y and substituted back in. So let's change this for x and substitute back into here. So this is x equals u minus y. So v becomes y minus 2u minus 2y plus 2y. The minus distributes in. And so v is, so 3y is equal to 2u plus v. So y is equal to 2u over 3 plus v over 3. Yeah, that's a better representation. All right, so I think we have our transformations here. We'll have u equals x plus y, and v equals y minus 2x. That gives us then x equals u over 3 minus v over 3, and y equals 2u over 3 plus v over 3. And now I want to transform the region to get my region in G. So we'll use a dark blue for G, I think. So there's U and V. And so now what I want to be able to do is look at my boundaries. So for my y boundary, I went from, let's see, on my y boundary, I had x equals y over 2. All right, I'm taking my boundaries here. No, I didn't have x equals y over 2. I had 0 to 1 minus x. 0 to 1 minus x. So 0 for x is u equals v over 3, or u equals v3. Let's look at our boundary equations. Let's put these out. So my boundaries in x was y equals 1 minus x, which I can translate into x plus y equals 1. So that was the 1 boundary, this boundary here. And now if I translate this, that's going to be u over 3 minus v over 3 plus 2u over 3 plus v over 3 equals 1. And let's see what happens here. Well, those two cancel each other out. And that gives me 3u over 3, right? Or u equals 1. So I have one boundary that u equals 1. All right, this boundary here was y equals 0, which is the same as 2u over 3 plus v over 3 equals 0, which is the same as v over 3 equals negative 2u over 3. Multiply everything by 3, and v equals negative 2u. So v equals negative 2u is the line starting at the origin with a slope of negative 2. That's v equals negative 2u. And then I need to look at the last boundary equation, which is x equals 0. And x was u over 3 minus v over 3. And so we'll solve this in terms of u over 3 equals v over 3, or u equals v, which is a line that crosses the origin with a slope of 1. And so it looks like my region G is here. There's G. And so we have our new region. So we can calculate our Jacobian and transform our space. So my Jacobian for uv is going to be partial of x with respect to u, partial of x with respect to v, partial of y with respect to u, and the partial of y with respect to v, the determinant of that. And let's see, the partial of x with respect to u, so let me bring in my x up here. So the partial of x with respect to u is 1/3. The partial of x with respect to v is minus 1/3. Right? Taking partials here. Partial of y with respect to u is 2/3, and the partial of y with respect to v is 1/3. Right, those are our partials here. These are all to the first power, nice and linear for us here. So I'm going to get this times this minus this, or 1/9 plus 2/9. What is going to get? 1/3, 1/9 plus 2/9. 3/9 or 1/3. So we have a scaling factor of 1/3. So now we can put all of our integration together. We can look at our original integral now. Which was 0 to 1 minus x, 0 to 1, x plus y square root, y minus 2x squared dy dx. And we can transform it where v is equal to negative 2u and v is equal to u. Let's see, make sure we're doing that right. How are we moving in our u direction? So our dv direction, so we move from this line, negative 2u, up to this line u in dv. And then from here, we go from 0 to 1 in u. We add our Jacobian factor, 1/3. And now we can look at our substitutions. We have u to the 1/2 power and y and v squared. All right, so we took these harder parts here and made these our uv substitutions so that this integration here would be easier. The trick became in our changing our boundaries. And so now I'll pull the 1/3 out. And we'll do v, so we're going to get v cubed over 3, evaluated from 2u to u, with du left over. Which is 1/9 u cubed minus 8u cubed. Oh wait, that was a negative 2u down here, so plus 8u cubed du. And I still had a u to the 1/2 out front. So that's 1/9 the integral of 0 to 1 of u to the 7/2 plus 8u to there's 9 of those all together, aren't there? Yeah. Should just add those together. That's what I get for not, right? Here we go. U to the 1/2. So if there's 9 of these, then I'll 0 to 1 u cubed, right? 9 of these, pull the 9 out front, times u to the 1/2, which is u to the 7/2 du, evaluated from 0 to 1, which becomes 9/2 u from 0 to 1 times 2/9, which equals 2/9. It's not a bad way of changing boundaries. All right, let's look at substitutions with triple integrals and look at how the Jacobian gets bigger.